Okay, those of you who haven't had me before, this is a set of video notes. The concept is pretty simple. Essentially, it's the same information I'd give you in class, except that we're not going to waste a bunch of time just listening to me talk in class. I'd rather help and watch you do the work in class. And I think you'll get by a lot easier. Some thoughts and complaints I've had about this is that it's really hard to stop and ask me questions if you're just listening to me on a video. I try to cover all of the information that I need to cover. So if you miss something, you're more than welcome to pause it, rewind it, go back, skip a little bit, whatever floats your boat. But what I want from you as you watch this is to fill out the worksheet that I gave you that goes along with it. There's just some pretty simple questions to make sure that you watch through the video. And then there's also some practice problems along with that worksheet. So in the notes today, we're going to talk about thermal energy versus temperature. And we're going to talk about our temperature scales. The first thing you know is what is thermal energy and temperature. Well, thermal energy is the total kinetic energy of a system. And that is associated with the random motion of the particles of whatever substance we're looking at. You should have learned that kinetic energy is the energy of motion, essentially. Well, when we have particles moving around, we call it thermal energy. That's the total amount of kinetic energy. Big idea, the more thermal energy we have, the faster those particles are moving. And the less energy, thermal energy we have, the slower those particles are moving. And that's pretty much in any given case, except for during phase changes when we go from a solid to a liquid or liquid to gas. And during chemical reactions, some weird stuff happens there. You know from experience what hot or cold is. That's a very qualitative measurement of temperature, but temperature is the quantitative measurement, which just means that we put a unit and a number to how hot or cold something is. And that's totally dependent on how fast those particles are moving, which is thusly, conversely, whatever, also dependent on the thermal energy that's present. Generally, in most cases, the higher the temperature you have, the faster those particles are moving, and whatever substance you're looking at expands or gets larger. The lower the temperature you have, the slower the particles are moving, and that substance contracts or gets smaller. Different substances can expand or contract at different rates, even when they're at the same temperature. So one of my favorite examples is a bimetallic strip, which just means there's two metals attached together in a strip, and if you heat it or cool it, it'll bend one way or another. I'm going to have to see if I have one of those in one of my cabinets somewhere, and maybe I can show you, because they're pretty cool. But we also have heat, and we learned about what heat energy is a little bit, or at least we learned an equation for it. But that is the transfer of kinetic energy between particles. Generally, when particles are moving at random, they tend to hit each other every once in a while. They collide, and those collisions cause a transfer of energy. And that transfer of energy is what we call heat. And you should have learned in earth science last year there are three ways to transfer heat or thermal energy: conduction, convection, and radiation. I don't think I have to teach you that in my class, so just make a useful connection to what you learned last year. There are three units of temperature that we're going to look at. One of them you should already be pretty familiar with. It's called Fahrenheit. It's developed in 1714 by Gabriel Fahrenheit, who's a German physicist. He was the first to use a mercury thermometer, which works by the expansion and contraction of the liquid inside that thermometer. Same idea as what we use today, except we use a different substance that is some type of alcohol. He chose the lowest temperature for the bottom of his scale. He chose the lowest temperature that he was able to make in his lab, which was by using water, salt, and ice. And that was the 0 point of his scale. For the other end, he used the temperature of the human body as it was known in 1714, which is about 100 degrees. And eventually the Fahrenheit scale was standardized in a way so that our freezing point is 32 and our boiling point of water is 212. That is stuff that you should have known by this time in your scientific schooling. There's also a scale called Celsius or centigrade. That was developed around 1742 by Anders Celsius, who was a Swedish astronomer. He wanted to make it very simple, like the rest of the metric system, where there's just some kind of power of 10 between important points. So there's 100 degrees between freezing and boiling points of water. Around 1948, they officially made that a part of the metric system and named it the Celsius scale. And most countries use this, except probably ourselves in Myanmar and Liberia. At this point, water freezes at 0 and boils at 100 degrees Celsius. So there's that 100-degree difference there. And a little easier to remember as far as boiling and freezing points. We also have a third scale called Kelvin. It's much less used and known, but we use it in science for a lot of important calculations. It was developed in 1848 by Lord Kelvin when he was only 24 years old. He was from Britain. He set the lowest point of his scale at 0, that 0 representing absolute 0, which is this crazy theoretical temperature at which it's so cold that every single particle stops moving. We've not yet reached absolute 0, but we've tried for it and came pretty close, but we haven't quite got there. And it has the same size of the unit, the same degrees are the same size as the Celsius scale. It's just that they're offset by about 273 degrees. So as you can see, if you wanted to look at how cold absolute 0 is, it's 273 degrees Celsius, or 459 in the negative variety, negative 460 degrees Fahrenheit. You guys have to know how to convert between temperature units, because that is exactly stated within the standard. Unfortunately, the dimensional analysis stuff that we learned isn't going to help us at all. We've got a couple equations that we have to follow. I would copy these down somewhere in notes so you have them for future reference. But here are some example problems. Let's say I wanted to take 59 degrees Fahrenheit, turn it to Celsius. I take my equation, which was Celsius equals 5/9 times the, in parentheses, Fahrenheit minus 32 degrees. So I take 59 minus 32, which is 27, and then I multiply that by 5/9, and I get 15 degrees Celsius out. Say I wanted to go 25 degrees Celsius to Fahrenheit, I would do the other equation. So I'm going Fahrenheit equals 9/5 times Celsius, and then add 32. So I take 9/5 times our 25. 25 divided by 5 is 5, times 9 is 45, so we get 9/5 times 25 is 45. Add 32 to that, you should get somewhere around 77 degrees Fahrenheit. And then if we want to go from Celsius to Kelvin, say I have 100 degrees Celsius, we take our equation, which is Kelvin is equal to Celsius plus 273. We do 100 plus 273, and by golly, it's 373 Kelvin. And last but not least, Kelvin to Celsius, we start with 325 degree Kelvin. All we do is subtract 273. And we end up with 325 minus 273 is equal to 52. That is it for this video notes. Let me know what you think. I hope it was at least somewhat useful. Don't forget to finish your worksheet. And that is about it.